With all of that intro now accomplished, I am very pleased to introduce Norm Jouppi. He is a VP for engineering and a fellow at Google. He's also the winner of the 2024 Cray Seymour Award awarded at the SC24 conference. And he is going to be your expert speaker today on unleashing the power of Google TPUs, accelerating AI, science, and data analytics. Thanks for joining us, Norm. Norm, you're
Thanks for inviting me. Yeah. And after the talk, I want to hear about that Arctic data center. It sounds like a cool place to run a computer.
Good fun there.
Okay. So let me try out the controls. Okay. So in this talk, I'm going to cover some of the key insights that we had in terms of building specialized supercomputers for AI. And one of the key things, you've probably seen the news about how different companies are saying they're needing 5 gigawatts of power or 2 gigawatts of power, but it's always a lot of power. So the first thing that we did was try to figure out how to get the power when we started the project 10 plus years ago as low as possible. And this is a diagram here showing a slide from Mark Horowitz's ISSCC keynote at the top computer, the top chip conference. And in it, he showed how the energy in a typical processor, say an x86, would be broken down. And you can see that of the entire 70 picojoules, there's only a tiny bit, like 1 picojoule, or sometimes even less, used for the compute. The rest is control, register file access, iCache access, stuff like that. So what we wanted to do is we wanted to get rid of all the stuff in the blue area. I think you can see my pointer, hopefully. And just stick with the red stuff. Right. So what we did is we had a long background in computer architecture, and different things have come and gone over the years. But if you keep them all, and I'm a bit of a pack rat myself, you have a toolbox that's stuffed with many different tools. And the tool that we pulled out was systolic arrays. Systolic arrays were developed in the late 70s and early 80s, primarily for signal processing. They didn't catch on widespread for computing at the time, but they're extremely efficient in terms of compute per power. If you look at the energy breakdown for this systolic array, you'll see that the add is most of the power. The whole thing is less than a picojoule. And so it gives you a huge improvement in perf per watt. So we decided to make heavy use of systolic arrays. The TPU version 1 had a 256 by 256 systolic array. That was integer, 8-bit integer going in, and then 16-bit integers coming out. So the way a systolic array works is you send in data. Here I've got some queues shown, but you don't have to use queues. You can read it out directly out of memory if the memory isn't a cache, but is a scratchpad memory, and that's what we have. And the data travels in one direction across the array, and then the partial sums travel down. And what's not shown in this figure is that at each intersection, there's a data value that gets multiplied with the data that's coming from the left and added in the flow that's going down to the bottom of the array. And for our first TPU, we also added a recirculating accumulator at the bottom, so we could accumulate more than 256 sums. The great thing about systolic arrays is wiring is done by abutment, so the cells basically don't have any wires between them. There's a connection on one side of the cell that it immediately connects to a connection on the other side of the next cell. And it avoids memory accesses, and I'll talk more about those later. There's no control logic to speak of, and it's only the adders and multipliers and the flip-flops to keep the data moving in sync. So there's really no overheads. So in late 2013, we started the TPU project. I joined Google to do the TPU project in late 2013. And we were able to show within about a year and a half to 2 years, tremendous performance improvements, both in terms of raw performance and performance per watt. And so this was a accelerator card that was plugged into our servers, and it was used for image recognition, speech recognition, things like that. And we waited a few years, and then we published the results in the ISTA, the Computer Architecture Conference, in 2017. So when we had done that, and we had taken some shortcuts to get it out as soon as possible to enable voice recognition earlier throughout Google products, the question was, what were we going to be doing next? Well, it kind of was a little bit of a surprise to us, but it shouldn't have been. I mean, a lot of things were surprises back then because the field was so new. That training was the limiter to further progress. So we had a pretty good inference system, but training was being done on CPUs and was running pretty slow. So we decided, contrary to people's advice, to build a training chip, even though other people thought it'd be too complicated to build. But we didn't stop there. We decided to build a supercomputer using that training chip. So that was a lot of fun. So the basic plan for what we called the TPU v2, even though it was quite different from the v1, is don't invent anything more than necessary. That was required to meet an aggressive schedule and a very small team. So that was kind of a blessing in disguise. It made a lot of design decisions simple. It's like, we don't have time to do that. Throw it overboard. So it's kind of going back to the Watson, IBM Watson quote about how 23 people, including the janitor, could build a supercomputer. So sometimes it helps to have fewer people. We did some other things that Cray 1 did. What we did was we started from a typical vector CPU architecture and added matrix operations. And I'll show a diagram of that on the next page. But that allowed us to keep the same architecture model of a system without the matrix operations, and there were, a lot of vector extensions to CPUs at the time. We didn't obviously implement those instructions into architectures, but that was the basic principle. And we wanted to heavily leverage a compiler because the ML workloads are a lot more deterministic than other kinds of workloads in general. Not a whole lot of branching going on. We used an 8 instruction VLIW baseline. I'd never done a VLIW before, but it seemed like the right thing based on all the units that we had going on in parallel, and also the lack of branches and speculation and all that stuff. So 8 instructions per cycle is a pretty beefy core on the scalar side. So here's a diagram of how Cray got to the Cray 1. So if you look to everything to the left of that vertical arrow there, this part looks a lot like the 6600 and 7600. These 2 previous machines. And then the Cray 1 basically added these vector registers and vector functional units. And so they were able to leverage code written for previous machines with small modifications to run on here to debug the machine, get it going, while they're working on compiler techniques and other things to get the vector operations working. So that's basically, we followed that same strategy. So part 2 was, once we have a chip, now we can fit the whole accelerator on a chip, but we need many of them to work together. How are we going to connect them to each other? So we borrowed a technique from later on in the Cray company's history, 3D tours used in the T3D and T3E. And the advantage of the torus is for regular computations, which again, ML tends to be fairly regular. People have experimented with sparsity, but in general, everything is like either big or small, dense matrices and some, vectors. So in that kind of environment, the data movements are very regular and follow the shape of the problem, the multi-dimensional matrices. And that allows you to make a lot of the connections with cheap copper cables between neighboring components. And so we took advantage of that property of the problem in building the interconnect between different TPU chips. This shows the scalability on real workloads at Google. It's published in a paper. A lot of these charts are published in papers, so they're public information. What you see there is numbers for TPU v4, which had up to 4,096 chips. Typically, we only use 3,072 because there were a few machines that were down. And you can see that up to 3,072, all the benchmarks except for 2 have basically indistinguishable from perfect scalability. The 2 that were dropping off earlier were recommendation models, and the recommendation models make extensive use of all-to-alls. So those make larger demands on the interconnection work. So they start to plateau around 1,000 chips. A third key insight, and really important for early adoption, was that training was currently being done on CPUs and GPUs using FP32. But Google's software infrastructure was basically truncating the FP32 values for storage to 16-bit values. And as someone who knows about numerics, that's, was a shocking thing, but it seemed to work for them. So when we were designing the machine, we started with the bfloat16, which is what they called the FP32 with the 16 lower order bits missing, brainfloat16 as the base data type. And if you follow how the BF16 value was used in the code at the time, they would use FP32 multipliers with bfloat16 operands that would produce effectively an FP24 value held in an FP32 because you get 24 bits from the multiply. And then they do FP32 accumulation on those values. So that's what we basically implemented in hardware. And the great thing about that is because they did that truncation on both CPUs and GPUs, and then followed it with the FP32 operations, we were able to maintain bit compatibility between CPUs, GPUs, and TPUs. So that meant we could get software up and running right away, and we weren't trying to, constantly figure out why we were getting different results. So this is the V2 here. It had 256 chips connected in a 2D torus. All the accelerators are in the central section, and the hosts are on the left and right edges of these racks next to them. It was air-cooled and not too dense of board design because we were more concerned about time to market. In fact, one of the most important things V2 did was it acted as a software development vehicle for future TPUs. Then, while we were working on bringing V2 up, we worked on V3, where we pushed the clock frequency higher and supported that with water cooling, and doubled the number of compute units and doubled the memory, and used optical cables for wraparound links. So it had 10x the performance of the previous version. So, and this one was responsible for a lot of the ML compute during its heyday. We followed that up with V4P, extended it from 8 racks to 64 racks, and also introduced OCSs, optical circuit switches. We called them Superpods. So here's an example here. You can look at the cubes. They represent different racks. The colors of the cubes represent the job that they're working on. And so you can take, with the OCS optical circuit switch, you can take wires from any one of the racks and connect them together into these geometric shapes to make rectangular prisms. And you can see that there's also a couple of gray cubes to the left, which are dead nodes. And so the nice thing about this is when you do have a failure in one of the cubes, it doesn't take down the whole machine. You can just not use it with the OCS switch. Let's say a few more words about the OCS switch. So each rack in the V4P is conceptually a 4x4x4 cube. And so if you look at it, you have 16 connections coming out in each direction on each side of the basically of an accelerator. So you have 48. Well, there's also multiplexing going on. So we you have the 96, but they're multiplexed down to 48 optical cables. And the cables that make the X connections go to X OCSs, and Y go to Y OCSs, and Z's go to Z OCSs. And so that way you can basically put the blocks together kind of like Legos in all three directions. And make the size of rectangular prism that is best for your particular problem. Okay, and the process of it can be quite dynamic. So as the training's going on, machines go down, some machines, they get new software installed. So we have an example here with 6 Superpods, and there's a bit of a video which shows how we can allocate different, basically one large job to 2 Superpods, but which actual Superpod it is can vary over time, and it also the individual ones used within the Superpod can vary over time. Oh, and this is a reminder that the communication between the pods is done via a regular data center network. So let's see if we can show the video. Okay. So the green squares are the ones that are doing the job that we're interested in. And you can see how the ones in each Superpod, can move around, the ones that are active on the job, and then the job can move between different Superpods as time goes on. And this is actually a job that took 56 days to run. So it's just a little mesmerizing to see. When you have a whole row of red ones, then it's probably a problem with the power, the bus bar, or something for that row. So it's by watching this, you can see what's going on in the data center. And then here's another video. Hopefully the sound will work. So this was for the V5P announcement, and which is 4+. And there's our TPU. Yeah, the data centers are pretty impressive when you go see them. I've only visited one once, and when you look down the aisle and you see like this little dot in the distance and realize that it's the person that's there. But we try to make use of the cleanest energy that we can get. So try to be good stewards in that. One of the ways that we can get more efficient operation is by using liquid cooling. And you're probably familiar, liquid cooling has been used in supercomputers for a while. And it was initially introduced in some models of the IBM 60 in the 60s. But the scale that we have as of last year in terms of water cooling is unmatched in the industry. So we have over a gigawatt of water-cooled systems in our data centers. And that gives us much more efficient cooling than trying to blow air and go through heat exchangers and things like that. So, and it allows us to run the equipment more reliably because there's a lot of failure modes that are exponential in temperature. And so by keeping the hardware colder than we have to, we can increase reliability. And reliability for these very large scale systems is, is an important and a difficult thing. So I'm going to take a deep dive for a little bit and talk about where all that power is coming from. So Bob Denard, besides inventing the one transistor RAM for DRAMs, he did some scaling computations, which showed that is now called Denard scaling. That's as the chip density increases. In the old days, the power would go down if the voltage was also scaled, and that's how we got from 12 volt MOS to 5 volt MOS to 3.3 and 2.5, etc. But now we can't lower the voltage anymore, and so we don't have this nice property of the power remaining constant while the compute goes up. And there's a quote from John Hennessy's Turing Award talk with a link to the video saying, "The end of Denard scaling is an equally important problem as the end of Moore's law, but it doesn't receive as much attention." So maybe now it's, with all the announcements of the gigawatt data centers, it's receiving more attention, but people don't know it's because of the end of Denard scaling. Here's a graph John Hennessy also showed at a plenary talk, and it's pretty dramatic because it's on a linear scale. It shows as time goes on, you basically just get a hockey stick in terms of power per square millimeter. So needless to say, that's a lot easier to cool with water, direct liquid cooling, as opposed to going through air and going from that air to water. When I was going over the costs of computing earlier, I didn't mention SRAMs. So SRAMs actually use a lot of power. If you look on this chart, you can do 16-bit floating point multiply for around 1 picojoule. But if you access 1 megabyte cache, that's 100 picojoules. And so one of the things that systolic arrays do is they give you great data reuse. So in a 256 by 256 6-solid array, you reuse the incoming data 256 times. So then that makes the compute the majority of the power consumption, as opposed to the SRAM or the wire. Since these charts from Mark Horowitz's ISSCC keynote have been published, computation has gotten 3x denser and lower power, but SRAM is still the same. So data reuse is really important for efficiency. Another tech trend that we're dealing with is the size of models was increasing by like 70% per year when we started, but it's just with AI really taking off, now it's going up to 10x a year. So memory capacity is also a significant problem. One way that people have tried to get more mileage, so to speak, for a given amount of data is use reduced precision formats. So we started out with bfloat16, that was reduced compared to FP32. Now FP8 computation is pretty common in industry. People are looking at using even smaller values. The problem there is then you can get inaccurate results, and it depends kind of what company or service that you're providing. At Google, when we make a mistake, 1 in a billion mistake, it can end up on the news as, you know, haha, Google said something that wasn't true. So for us, accuracy is very important. And so we've been a little less hurried to jump into the lowest precision formats like 4 bits than some of our competitors. Also, you can imagine if you're trying to train a system with, you know, 100,000 GPUs or TPUs or whatever, reliability, availability, and serviceability are big things. And supercomputers been dealing with that for a long time. And we can reuse a lot of those classic techniques, which is good. So we do, you know, local and global checkpointing. And just like with supercomputers, silent data corruption is a problem. And I don't know how many of you are space flight fans, but I grew up during the Apollo era, and I like reading the books about the space program. And Gene Kranz's failure is not an option. And for us, compared to silent data corruption, failure is a good option. It's better than not knowing you had a problem. So we do a lot of work on screening, screen components for automotive standards, and put in a lot of checkers and double chip kill DIMMs and stuff like that, so to prevent failures from happening. And so to summarize, the research in AI is advancing at a tremendous pace. It's really shocking how quickly it's improving. The things I'm most excited about AI are not being able to chat with someone or something at any time of the day, but I think a lot of good will result from its application in science. So, for example, there was the protein folding by Google DeepMind. There's power tools for the modern world, like image-based language translation. When my family and I went to Japan 2 years ago, and we held up our phones with Google Lens, and it would immediately translate the Japanese signs to English for us. So we didn't get lost too often. And I think areas for future research are the AI systems are scaling to be even larger than traditional supercomputing systems. We're talking about Yada and Rana systems. And so RAS will become even more important. And the models are also starting to get more complex, like mixtures of experts as opposed to monolithic models. So it's a very interesting time at many different levels. Okay, that's it for my talk today.
All right, Norm, thank you very much for that great talk. We are going to move to Q&A now. So I'm going to start with the first question while people start submitting their questions into the session. The transition to bfloat 16, you made a great technical argument for why that was an important thing to do and an optimal thing to do. There's a big discussion going on in the HPC community, the traditional HPC community, the simulation community right now, about how, well, if we have to ride the backs of AI optimized hardware, we better learn how to use lower precision in more of our classical HPC workloads. Have you done any work on this specifically in terms of helping people understand, where bfloat 16 can and can't, where the parameter space is for where it can and can't help in different simulation-based workloads? And is there anything afoot that you could share for simulating a higher level of precision with TPUs?
Yeah. So when we were picking a numerics format, I actually went to the HPC literature and found, I think it might have been some folks at PNNL who were investigating use of lower precision arithmetic, mainly single instead of double, but some even smaller. One thing about the bfloat 16 support that we have is we have different modes where if you're familiar with school book multiplication, where you have like 1, 2, 3 times 4, 5, 6, and then you do pairs of operands, and then you sum at the bottom. You can do that with our bfloat 16 hardware. It was designed so you could compute FP32 values by doing a series of smaller bfloat 16 computations.
And so what's the performance overhead for doing that? I mean, as you well know from your Cray days, the traditional overhead is, you double the number of bits of precision, you have the performance. But when you do it in software, it's often worse than that. Do you have any sort of guidance for folks who might want to use this great hardware, but occasionally do 32-bit, what the performance overhead might be?
Yeah, it depends how accurate you want it to be, because if you're multiplying the most significant digits, then you can, the cheapest way to do it is basically the same cost, but only use the high order 8-bit mantisses, and then the next one is to do the highest order times the middle byte, and so then that adds like 4 more, and then if you want the exact thing, then you have to do the least significant bytes as well. So a lot of times in our algorithms we cheat a little bit, because we might be going to a bfloat 16 value at the end anyway, so there's no point in getting all 32 bits correct. So it varies depending on the algorithm's needs for precision. Anywhere from 1 to 9 is basically
from 1 to 9. Okay. Let's see. We got a question here from Deepak Suresh, thanks you for a great presentation. You have shown about the lithography trend and the reduction of power in TPUs. The same is happening in traditional CPUs, GPUs as well, this end of Dennard scaling, et cetera. What are the power consumption characteristics of TPUs compared to traditional HPC hardwares? He adds for the same computational workload, but I think obviously we're going to confine that to deep learning training workload, since that's where you probably have the best data on TPUs and energy consumption per flop. So what is the relative energy efficiency comparison to CPUs and GPUs for the workloads that TPUs are optimized to run?
The most recent data is in ISCA paper from 2023, and it shows that the TPU is V4 is 2x more power efficient than the GPU that is similar generation. The V1, because it was an inference only machine, it was in its paper, the 2017 paper, it showed much higher improvements, like factors of 3,200 more energy efficient.
So for V4, it was 2 to 1. Do you have any sense for how that is keeping up with V5 and V6 versus latest generation GPUs and CPUs?
We're as part of having a small team, we didn't have a power team for a while, so we're just kind of like, it was Wild West. So, but now we have some good power engineers, and I think we'll make further relative improvements compared to other competitors.
And I'm going to ask, you hinted at it in your presentation, but I'm going to ask the obvious question: is Google using these TPUs for all or most of its in-house AI training?
Yeah, for most of its internal training. Yeah.
All right. Let's see. We have another question here from Diarmio Buckley. What is the likely change in engineering choices if multimodal use cases, like your Japanese tourism case, really take off?
It's really not that different. So, I mean, you have a convolutional network on the image, but it's still a neural network, and then the language translation is a LLM. So, but when you have a composite model, that makes it much more powerful and useful. You can do like one of those screwdrivers where you can change the blade and change it from Phillips to regular. Yeah.
All right. We have another question here from Guru Rangavital. You mentioned mixture of experts could be one of the frontiers for AI advanced computing. Curious, do you see hardware-driven improvements, or more the method of training and instructing LLMs will drive innovation?
Well, I think that the software is the primary driver, and it's our job to accelerate it. And so you have to start out with something that's relatively efficient in the software first, because there's only so much you can do in the hardware. So the mixture of experts, you wanted to support all the new models that do make a significant difference. And for a mixture of experts, it requires more communication than traditional monolithic models. And so there's more reliance on interchip interconnect.
Right. And I'll ask a question again. Do you have any, can you say anything about future plans for this? Like in the era of quantum computing, which has lots of hype as well as wonderful results, they're starting to share their plans. Many of the vendors are sharing their plans 4 or 5 years out. And of course, there's incentive to do that. You're trying to make sure you have investment for roadmaps that are 5 years out. But I know Google, we keep things closer to the vest. But is there anything that you can say about next generation TPUs. That's not non-disclosure.
I'd just say that even though things are getting harder with Moore's law slowing down Denard scaling, there's no end in clear sight yet. So I think we'll have dramatically improved systems for many, many years still.
Great.
Which is exciting.